All right, so last time we were talking, starting to talk about how to make an LNA, and the first thing that we did was we determined that the input impedance of an LNA matters a lot in terms of its noise performance, and we started now trying to figure out how to actually achieve an input match for an LNA, and we looked at this first option, which was just to add a shunt resistor where the shunt resistor was equal to whatever our source resistance is. And, ultimately we came to this, we did a conclusion that this doesn't work so well in terms of the noise performance. So we have this portion that we found here. Where the noise figure or noise factor is equal to 2 plus this excess portion, and so ultimately we understand that excess portion there is going to be larger than 0, and that means that the noise figure minimum for a resistive matched LNA is going to be 3 dBs. So let's look at some other options. All right. So here's our next option. Our next option is let's look at a common gate stage. So if I look at a common gate stage, what is the impedance looking into the source terminal? I'm not hearing anything, so maybe my audio is
1/GM. Yeah.
Yeah, there we go. My audio is not so good. So I was the problem. All right. Yeah, it's 1/GM. All right, so that's good. We have a real portion of the impedance that we can rely on. So we have something, a resistive impedance that we can match to. So let's look at our noise model for the common gate circuit. All right, so we have our source resistance, and we know that this is going to come with a noise current source. So this is going to be IS squared is equal to 4KT over RS times the bandwidth, delta F. And we also have our channel noise source. This is IND that we've been looking at already. All right. Now, what we're going to do to simplify this analysis is we can split. If we look at the source current source, part of it is going into ground, so we can redraw this. So here we have IS squared. And then if we look at the drain noise, we can also redraw that. So we can put the noise on one side of the circuit and on the other side of the circuit. These are equivalents. And this is our resistance 1/GM. And ultimately, we're trying to figure out, how much of the noise current flows into the short circuit at the output here. So we're trying to find I squared. So let's look at this at the noise due just to the source. We have a current division. Now let me ask a question now. My laptop switched to using this dark theme. and I was looking at it, and I was thinking, the contrast is actually better than the one I was using for my notes. Can I get a quick survey? What do people think of the colors right now? Indifference? Utter indifference?
No, I think the chat is coming in as positive. I'm not sure if you can hear this, by the way.
I can hear you. Yeah. I heard Peter, I think. I think that was you, Peter, right?
Yeah. And the chat says they like it. Yeah.
Okay, good. It's hard for me to look at the chat at the same time as the camera and all that stuff when I'm not in front of a bigger monitor. Okay. All right. So anyhow, we have the noise due to the source, and now we have to figure out the noise due to all sources. So of course, the first part's easy. We just found it. Okay, and now we have our drain noise portion. So here we split our drain source, our drain noise source, into two sources. So there's one portion that's directly tied to the output, and another portion that's going to experience some type of current division. And if we add all that together, we're going to find that it is something like this. Oops, not squared. All right, and then as we did when we looked at the common source stage with the resistive input termination, we're going to find the noise due to all sources divided by the noise due to just the source, and take the ratio of those, and that will be our noise figure. And for this case, if we make all of our substitutions, we're going to find that this is equal to something like 1 over gamma times GDO divided by GM. And of course, that ratio of GM to GDO is called alpha. So the noise figure is 1 over gamma divided by, 1 plus gamma divided by alpha. Just recalling that GM divided by GDO is equal to that parameter alpha that we found earlier. All right, so this is kind of an interesting. This is pretty interesting because what can we say about the frequency shape of this noise? Is there any parameter in there that has a dependence upon frequency? At least to a first order. Yeah, to a first order, we don't have any frequency dependence, so that's something nice. Now, in general, what we'll find is that a common gate stage has higher noise at low frequency than a common source stage. So we tend to want to use a common source stage, but here we have we have a means to present a real impedance, which means we can do an impedance match, and the noise figure of the amplifier has a flat response with respect to frequency to a first order. All right. Any questions there?
Yeah, sorry, this is a little embarrassing, but I've gotten a little lost. I forgot what gamma and alpha are.
Oh, so alpha is just the ratio. If you remember, for a long channel device, GDO is the conductance of the channel at zero bias. And if you recall, for long channel devices, GDO is equal to GM. So alpha is 1 for a long channel device, and it's something bigger for a short channel device. And gamma is just a parameter of the device. Let's see if I can tell you where we talked about gamma to remind you.
It's okay. I can find it in my notes. Thank you. There's second order parameters, so I forgot that. Thank you.
Yeah, no worries. I just want to point it out for everybody because it actually is a good question. And I know it's in the notes somewhere, just to point out where it was, but anyhow, I'll find it in just a bit and point it out in the chat. I don't remember where we covered it. Okay. Yeah, the important point to note though is that these are just parameters that have to do with the device itself, and they are dependent upon the channel length of the device, but they are not dependent upon the frequency of the device. So the common gate gets an independent with respect to frequency noise figure. Okay, so we're going to go on to our last element, or our last effort to provide a resistive match in common source amplifier. So the first one was fairly easy. We just hung a resistance off the gate, called it good. What we're going to try and do now is to synthesize a real impedance. All right, so imagine that we put some impedance, we'll just call it ZS, in the source of the transistor. And then we're going to monitor what the input resistance or input impedance Zn is. And to do that, of course, we go to our small signal model. So here's our small signal model. It's just a pi model. We put a resistor ZS in the source, and we're going to put a test voltage source, Vs, at the input, and we're going to measure the current Is that flows into the circuit, take the ratio of Vs over Is, and that will tell us what Zn is. This capacitance is between the gate and the source. This is a CGS capacitance. And so let's look now at what Vs over Is is. Well, we can, basically assume we can basically solve for a KCL at the source node and solve that node. We can find that our impedance is going to equal ZS times 1 plus GM divided by S times CGS plus 1 divided by ZS times S times CGS. All right, so we have a couple of cases that we can try here. What happens if we turn ZS into a resistance? And in particular, let's just make ZS equal to RS. We want a purely real element there. All right, if we do that, Zn is equal to RS plus GM times RS plus 1 over S times CGS. All right. Now, what does this look like? What if I were to ask to draw an equivalent circuit, what's my equivalent circuit? We definitely have a resistor RS, right? And this portion here, it just has the same impedance as a capacitance, right? It's inversely proportional to frequency. So this looks like a capacitor. In fact, it looks like a capacitor whose value is equal to CGS divided by 1 plus GM times RS. All right. That actually, this can work for us, right? If we wanted to achieve an input match here, we have a purely real term. So we have a real term that we can deliver power to, and of course we can add some other component if we wanted to tune out the capacitance that we see. What would be wrong with using RS in this source? Why wouldn't we want to do that?
A limited bandwidth.
It's not going to impact the bandwidth directly. Now, indirectly, because we have a reactive component, still we're going to have to do something to tune the bandwidth, but not the bandwidth directly. But let's look. Anytime I'm adding a resistor, what am I doing? I'm adding an extra noise source. So I don't want to do that. All right. Next option, and let's add a reactive component to avoid adding noise. And let's add some capacitor. We'll call it CS. All right. If we added a capacitor and we redid this math, we'd find that Zn is equal to 1 over S times CS times the quantity 1 plus CS over, sorry about that, over CGS minus GM over omega squared times CGS times CS. All right. Anybody, what's wrong with this circuit? There's something glaringly wrong with it.
It's still capacitive.
Well, it's still capacitive, so we didn't really fix that portion. But even more importantly, what does this sign mean?
So negative real impedance. I mean negative real impedance. So
It's a negative real impedance, right? And that means a negative. We have a negative resistance here, right? Okay, a negative resistance. Now, this is a negative small signal resistance here, but a negative resistance implies that we could have some potential problems with instability. Now, we'll look at this later on in the class, but the way that we make oscillators is to make a negative resistance, at least a virtual negative resistance, using some type of feedback, and then we try and make that a precise value that is conducive to starting up an oscillation. With an LNA, we don't want it to oscillate, so this is not necessarily a good option for us. All right, so our last option, of course, is to add an inductor. Let's say we add an inductor that has a value of LS. And if we work the math out now, we're going to find that it's equal to SLS plus 1 over SCGS plus GM LS over CGS. All right. So what do we think of this? This is pretty good, right? We have an inductor and a capacitor. So they have opposite signs for their reactance, and that means that we can find some, resonance. If we play our cards right, we can, we can size LS so that it resonates perfectly with CGS. And if it doesn't resonate perfectly with CGS, we can add some excess capacitance to tune it. And with this value, we can set this term equal to RS, right? So we set GM times LS over CGS equal to RS, and we have an impedance match at the input. This term GM over CGS, where have you seen that before? Anybody remember?
Oh, it's the gain.
It's not gain. It's not gain
it's I think FT. It's FT.
Yeah, you're right. It's actually omega t, but because we haven't divided by 2 pi. But you're absolutely right. It's the transition frequency. All right. So interestingly, that's more or less a constant for a given process. So if we want to tune the design, we size LS so that we get an impedance that's equal to RS. And then we try and add some capacitance to get a resonance. All right, and indeed, that is how we make a resistive match. Now, it's fairly common to use a common source amplifier. In fact, if you look at most LNAs, they probably use more common sources than anything. The reason for that is fairly simple. Especially at low frequency, the common source amplifier is going to have better noise performance, and typically it also has better gain than the common gate amplifier. But there is some advantage to having that flat noise performance with respect to frequency that you see in the common gate amplifier, and so they are used at times. Okay, so if we want resonance, we set SLS equal to 1 over SCGS, and that means that our operating frequency would be equal to 1 over the square root of LS times CGS. All right. Now, if we want to match at another frequency, so this is fairly limiting, right? We'd have to, if we wanted to change the frequency of operation. Remember, we're picking LS based upon GM over CGS. So if we want to change the frequency of operation, we'd effectively have to change the device size in order to change CGS. That's somewhat limiting. So if we want to match at a different frequency, we can modify the circuit slightly. So for instance, we can add an extra component. Let's just say we add an inductor. We'll call it LG for gate inductance. And then we find Zn with this extra component added. Of course, we can quickly look at Zn. It's equal to Gm times Ls over CGS. That doesn't change because adding that series inductor is not changing the real part of the impedance. So the only thing that does change is our reactive portion. So here we have the series combination of LG and LS. And then we have our capacitive portion. All right, and now our operating frequency omega naught is equal to 1 over the square root of LG plus LS quantity times CGS. Now, I'll also add, we could do a combination here. For instance, we could, if we wanted to add another component, if we wanted another degree of freedom just to play around with, we could add, some additional, gate capacitance here if we wanted to be able to tune more independently. All right, so what does our equivalent circuit look like now? Well, we have the real portion, and this is equal to omega t times Ls. We have some capacitance. This is equal to CGS, and maybe if we added some CG, it might be there. And we have this inductance, and this is equal to Ls plus Lg if we add that. All right. Now, we have a series resonant, ultimately we have some type of series resonant network, right? We have a resistor in series with a capacitor and series with an inductor. So we can also talk about the quality factor of this network. What's our quality factor for this network? It's going to be omega times Lg plus Ls all over Rs plus omega t times Ls. We can make some substitutions here. All right, so there's our quality factor. And now, what's interesting, when we talk about resonant circuits, and I don't know if we talked about it yet in this class, oftentimes when we talk about resonant circuits, we make a statement that says, well, at resonance, the capacitance cancels the inductance. And while it's true that to the outside world or to the outside observer, the impedance of the capacitor is exactly equal, to the negative impedance of the the impedance of the inductor is exactly equal to the negative impedance that the capacitor presents. And so to the outside observer, there's no net reactance at the resonant frequency. But the reality is that essentially what's happening is you're trading energy back and forth between the inductive element and the capacitive element. And the voltage across the capacitor or the inductor can be bigger than the external voltage in the circuit. All right, so let's look at our equivalent circuit again. We have our resistor, omega t times Ls, our capacitor, CGS, maybe plus some excess CG, and we have our inductor. LS maybe plus LG if we add that. All right. Now we know that the voltage across this entire circuit has some value V out. And we also have the voltage across the capacitor. This is equal to VGS. All right. So we said just a moment ago, at resonance, XC is equal to minus XL. So the impedances are canceling one another. And ultimately, the voltage across the capacitor and inductor are going to be equal and opposite. All right, and they're going to be equal to Q times VI. So the local voltage across the capacitor or the inductor are equal to Q times whatever the input voltage is. So let's now make some substitutions. So we know that RS is equal to omega T times LS if we have an impedance match. So we know that VO is just the voltage division that happens between RS and the tank impedance, and we're looking at this at the resonant frequency. So this is just a pure voltage division. All right. And now we're doing this to try and create an impedance match. So we know that omega T times LS is equal to RS, and that means that VI is, or that VO is equal to VI over 2, since this would just be RS divided by 2RS. All right, so if we plug this in, we know that voltage across the capacitor is equal to VGS. We can say that VGS is equal to 2 times Q times VO. All right. Now, what is the drain current that flows in a MOS due to the gate to source voltage?
Is it the saturation current?
No. Let's think a little bit simpler than that. It's equal to GM times VGS.
GM, VN. Yep.
Yeah, GM times VGS. Yeah, we're in this case it would be equal to VN, right? All right, so we just found that VGS is equal to 2 times Q times V out. All right, now we're going to define a big GM for those of you that have taken my analog course before, we know that of the device. Big GM is the transconductance of the device plus all external circuitry. All right, so big GM is equal to DID by D.
Excuse me, Dr. Walling. Your
Yes,
internet
sir.
is not stable. It's prefer your video should be close.
Okay, I can stop my video. Is anybody else having problems with it?
Yeah, so basically for the past minute, all of your audio has come through mostly, but the video is frozen. Both your camera and your screen share have been frozen.
Okay.
We've been hearing you talk
let
about
me-
Big GM.
Okay, I'll recap it then. I'm going to turn my camera off then for the time being. We'll see how that goes. Oh yeah, I can see for some reason my connection went really bad. All right, well, hopefully that gets fixed. We haven't covered fading yet, but this might be a good example of fading.
Yeah, try moving your laptop 1 centimeter to the left.
I did, and all of a sudden the signal's better. That's great. Yeah, I mean, my laptop also has multiple antennas on it, so we should also be getting some improvement from diversity as well. But nonetheless, okay. So just to go back, we were talking about transconductance. So we have this term little GM. This is the transconductance just of the device. So if we look at that small signal pi model that we looked at before, this is the GM that's associated just with the transistor itself. And big GM is the transconductance of the device plus external circuitry. And we normally define these really the same way. Little GM is defined as DID by dVGS, where we don't have any external circuitry. And big GM is going to be defined as DID by some other voltage. Now we know that in this particular case with this resonant circuit, VI and VO are proportional to one another. So I'm just going to say DID by DVO for convenience, just because they are related to one another by our, calculation that we did earlier. More or less, we can say that the big GM of this device is equal to 2 times Q times little GM. All right, so what is this telling us using our inductor trick to synthesize an impedance? Well, we get free gain, right? So ultimately, the way any transistor amplifier, or at least most transistor amplifiers, work is that the device to a current, and then we run that current that's produced into that. An impedance in the source. We're actually adding a degeneration to the transconductance, which means that the transconductance actually gets less. But in our case, because we have this resonant circuit and we get this magnifying effect on the voltages because of the quality factor of the tank, we essentially get free gain in our circuit. Now, this is gain in a narrow band, right? Because it only works, where the circuit is resonant. But in that narrow band of interest, we get this free gain. So another positive of using the common source amplifier. Okay. Any questions at this point? All right. Now, what I want to do right now is pause for a moment and talk about and do a little bit of do a few examples on cadence because you have some homework coming up. I'm going to show you a few tricks that we can do. I'm going to open up. while this is opening up, how have folks been able to get their Cadence open and working pretty well?
Yeah, I was able to start up and run an S parameter simulation. I just forgot how to do it properly. But yeah, Cadence actual software is working.
Okay.
Yeah,
great.
I was on earlier today and didn't have any issues.
Perfect. Okay. Yeah, let me know sooner rather than later if you ever find issues. The ECE cluster is far from perfect, and so it will definitely freeze up from time to time. And so if you ever spot any issue, just let me know, and we'll try and get it fixed as fast as we possibly can. Okay, when you open up Cadence for the rest of this class, I think I set it so that you should be able to see this ECE 5984_RFIC library. And I am going to add homeworks and examples into this library throughout the course, so if you have questions about certain things, you'll be able to look there and hopefully see some examples. All right, now one of the homework problems is going to have to do with copying something from the first homework and repeating it. I'm going to kind of show you how to do that quickly. So we have here, homework 1-1A. I'm going to right click on it and I'm going to click copy. And I'm just going to rename this homework 2-1A. And I'm going to open that new schematic. All right, so this was just a simple matching network that we did. And now we're going to be doing, we can do something like a comparison here. So I'm going to press C for copy. I'm going to draw a box around the circuit. And I'm just going to select all elements. I'm going to click on the circuit in some place, and I'm going to place an exact copy of the circuit right down below. So now I have 2 of these circuits. And in the second circuit, we're talking about using real components. So I'm going to insert a component here. I press I. And I'm going to go and get a component from the library. Now we can do this in a couple of different ways. So for instance, if I just highlight the library and I start typing CMOS22, the various libraries will come up. There are inductors in the RF and millimeter wave library. I'm just going to grab one from the RF library. If you don't remember what the inductors are called, sometimes you can start typing IND, and indeed an option for an inductor will pop up. You'll see a couple of inductors, and we'll look at the layouts, and we're going to talk about passive circuits in a few days. But INDP is what we call an asymmetric inductor. It's basically just a spiral that's wound in upon itself. And IND Balun or IND transformer, these are different versions of transformers that we can make on chip. And SIM and DP is a symmetric inductor. All right, well, I'm just going to grab INDP for the purposes here. And one thing that you'll notice with this is that there isn't necessarily an easy way to correlate the I should say the inductance to the geometry, at least directly. There is a tool here that I'm not sure if it's working right now. Let's see if it is. Find optimal inductor. It might not be working. We're actually getting the PDK upgrade or updated right now, so that tool might not work. So we might have to iterate a little bit. So let's see, what size inductor did we have in our design? We had something like 530 picohenries. All right. And what frequency were we doing that at? Was it 6 gigahertz, as I recall?
Yes.
Is that right? Okay. All right, so we're going to put a frequency of 6 gigahertz in, and then we can change the inductance by changing the diameter, the width, or the number of turns. Generally, as we increase the diameter, the inductance will go up. As we decrease the turn width, the inductance will go up. As we increase the number of turns, the inductance will go up. We're not going to worry about shield options for the time being. That generally will only affect the self-resonance of the inductor. All right, so we need 531 picohenries. Let's see if we can just make this by making a very big inductor. Well, it told me that I went too big up, and for some reason the callbacks are also not working. Model playback has expired. Okay, well, this is going to be fun. All right, so I do see something that I need to fix, but nonetheless, if you keep iterating through this, you'll eventually find one that will work. In the meantime, I will find something that will make it easier for you to do your homework. All right, and as a result of finding that happen and the homework is due in 2 days, I will extend the deadline of the homework.
So, Dr. Wang, does this mean we should be using these components to do the S-parameter simulations instead of just the analog lib?
Well, I believe that, so the first homework I said to use only analog lib, and then in the second one, I believe that I have at least one element where you're having to use the library component, right?
So as far as I know, this homework that's due on Wednesday, it just says to create the matching networks, and it doesn't specify which library to use. Someone correct me if I'm wrong.
Oh, no, but oh no, you're right. I think I did say to use Q though, to use a quality factor. Was that what I did in this one?
It says add resistance to the inductors until the quality factor is 15.
Ah, okay. Even easier. All right. So I was building quite naturally. So next week we'll be using real kit components, so I have time. Okay. All right, so we're going to add, so we want to make the inductor have a quality factor of 15, right? So in this case, we know that quality factor is equal to reactance over resistance for a series RL circuit. So we want a quality factor of 15, which means we do 2 times pi times 531 picohenries divided by 15. And this means that we should have, 2 times pi. Yes.
If you write in your OneNote, we cannot see that.
I'm not writing in my OneNote. I'm just calculating really quick what the resistor needs to be.
Okay.
All right. So what we're doing here is 2 times pi times the frequency, 6 gigahertz, times the inductance, 531 picohenries, divided by Q is equal to the resistance. That turns out that this should be something like 1.335. Now, there's no need to go to absurd precision here. We've probably gone to far too absurd a precision, even just going out to the 3rd decimal place, but that's okay. All right. So if you'll notice, the component itself, if we're looking at the properties, it has inductance and resistance. This is a series resistance. Now, if we wanted to, I could have inserted from analog lib a component called res, and I could have given it that 1.335 value. And I could have put it into the circuit need to delete the wire that's shorting it. In that case, I would make the resistance of the inductor 0. Either of these is fine. There are pros and cons to doing both of these. Okay. So let's check this out. I had a few questions about how to measure the 3 dB frequency and the 10 dB frequency that came to me via email. All right. So here's our Maestro view. The S parameter simulation is already set up, but we've got 2 additional ports now on the schematic. Now it just adds those sequentially. So I'm going to go in and add port 2 and port 3. So now we have ports 0, 1, 2, and 3 in our port list. And I'm not going to change anything else. We're still doing the same frequency range. We're just going to see the impact of measuring, of adding the Q to the component. Go ahead and save frequently. All right, now let's run the simulation. And one of the things, so what this is going to do is it's going to run a 4-port S parameter simulation. But what what we're really doing is doing 2 independent 2-port simulations. So normally when you do an S-port simulation, the ports might have some relationship to each other. In this case, what we're doing is just trying to be able to do a direct comparison between the LC network on the top and the LC network on the bottom, or the RLC network on the bottom. So I'm gonna run that, and we're gonna see what happens.
Sorry, can you say again how you specified that you don't want to like any interaction between the top and the bottom?
You don't have to. It's really, if I go and look at this circuit, there is no physical connection between port 0 and port 3 or port 2. There's no physical connection between port 1 and port 2 or port 3, right? So you don't have to specify it. In this case, it's just how it's drawn.
Thank you.
Yep, no worries. All right. So now we had already had the simulation set up. Plot S11, S21, S22, and S12, and we're looking at the impedance, the S11 and S22 on the Smith chart, because those are really relating us to an impedance, and the Smith chart helps us to relate these things to impedances in a more easy fashion. All right, now let's see, how do we add, or the new simulations? Well, in this case, so port 0 was our one port. Port 2, or port 1 here, was our 2. Equivalently, we're saying port 2 is 3 and port 3 is 4. Everything is indexed back to 0. We could change the names of those things if we didn't want it to be, if we got confused. You can always go in and just change the port name to whatever you want it to be. Let's see if it has an. All right. In the conference hotel with a lot of engineers that are using all of our bandwidth right now, so blame them all. Okay, let's go into Maestro and go to results, direct plot, main form. The other day, also, this is why it's great to do this live. I get to see all the mistakes I made. So one of the things that I forgot to do was I copied the Maestro view, but I did not change the design name. So if I right-click on this ECE 59, where the design name is, and go to design, I need to update this and have it point to the new problem, not the old problem. All right, so now that I fixed that, if I run this, let's see what happens. All right, so it ran pretty quickly. Now we'll go back to results, direct plot, main form. So now you can see that we have S 1 1 1 2 1 3. So and then anything above the 3-port design, you have to use these drop-down menus, right? So we know that S11 and S33 are should be related to one another. One is the measurement without any additional resistance, S11. So let's plot S11. And S33 is for the circuit that is equivalent to S11, but it's for the circuit that had our added resistance in it. All right, so you can see now that that adding some resistance did indeed change the circuit performance a bit. But not too bad. The match is still pretty good. In fact, if I look at the bandwidth, remember we're saying like the minus 10 dB bandwidth is about equivalent, is the good number. You can see that the bandwidth didn't change very much. Center frequency shifted a little bit. Bandwidth changed a little bit. The Q of the second circuit is a little bit lower. And that means that its bandwidth ends up being a little bit wider as a result. All right, let's also look S21. We already have plotted up there, so I could just click S21 if I wanted to. But S21 is equivalent to the same thing as S43 in our lossy circuit. All right. Now you can see, a little bit of difference, right? S43 is our circuit that has a little bit of series resistance. So you do expect to see increase in the insertion loss. If we put our cursor over it, you can see that we have just about a half a dB of loss, whereas the ideal circuit was, basically no loss. So that's good. You can immediately see some difference. Now, it's a little bit hard sometimes to look at S11 and S21 on the same window, so I can always go up to File, New Subwindow, Rectangular. I can add a window, and I can drag the measurements. For instance, I'm going to drag S43 over to the new subwindow, and I'm going to drag S21 over since I'm comparing these. You can now see a bit more of a dramatic comparison just because of the scale difference. And now I can do the following. I'm going to create a marker. I'm going to attach it to the trace S43DB20. I'm going to actually do a horizontal marker. And I'm going to, we were asked about this finding the minus 3 dB frequency. So I'm going to have it down minus 3 dBs from the peak value, which is 0.557. So I'm going to make this minus 3.557. I'm going to click apply, and it will now tell me the frequencies where it crosses over the minus 3 dB point. you can see from this that, of course, it does not cross on the lower end. So, what do we choose for that lower end frequency? Well, we just probably stick with 0. That would be a start. In many instances, you'll find a low frequency and a high frequency value where it crosses over. But if it doesn't, then you just go with 0. If we go back to the reflection coefficient, remember we were talking about the bandwidth in terms of the 10 dB. The minus 10 dB crossing points. So here we can change these to minus 10. Oops. I'm going to click apply. And oops, I forgot to check that that did not get changed back. It's 10. So you can kind of see the reflection coefficient bandwidth of the circuit. The reflection coefficient bandwidth of the circuit and the transmission coefficient, which would correspond to S21, don't always correspond to one another. The way that the resonances work, sometimes you have gain or at least lower loss across a different bandwidth than your impedance match is good. Okay, any questions on the mechanics of these simulations or anything like that? Okay, not hearing any. All right. I think we're at a good stopping point because we're going to start talking a bit about gain and stability in the next. So I think we'll go ahead and stop here unless there are any strenuous objections.
Sorry, I was just wondering if you could repeat again what you said about crossing at 0, because I'm seeing like how we estimate the Q. It's like the frequency at the high and the frequency at low. So if we substitute 0 for one of those, wouldn't that make the Q 0? Like our approximation of Q that you
No,
gave
because
us.
it's FH. It's FH. It's FH. It's the crossing point at the high frequency minus the crossing point at the low frequency divided by the center frequency. So it won't be 0.
Okay. Okay. Thank you.
Yeah. Okay. So I apologize. I did not take my office hours out of the calendar. It's just because they happen to coincide with meetings that I've had at the conference. If you do want to schedule an office, a meeting with me, please email me, and that works for both of us to talk individually. But that will also apply for tomorrow. I will. I'll do my best to find a time if you want to chat. And I apologize for so much travel in the early part of the semester. Just the way that it worked this year, and hopefully we're making up for it with the virtual lectures. Right. All right. With that, I will let everybody go. And please message me if you have any need to have a meeting. All right. Talk to you later.
Thank you.